standard that we're looking at today, what happens when different types of stars die. So I would like you guys to write down our question of the day. What determines how a star is going to live and how it's going to die? I would like you guys to start off by making a flowchart in your science journal. You're going to have one section for high mass stars, one section for low mass stars. It's going to look something like this. So take a moment and copy this into your science journal. And now we're going to go through each one of these stages and try to figure out what is happening. First section is a stellar nebula. That's a big cloud of gas and dust. There you go. It's what provides all of the materials to start a star. Mostly gas, mostly hydrogen that is in a star comes from a stellar nebula. That stellar nebula condenses because of gravity and turns into a protostar as soon as fusion turns on. As soon as fusion turns on, but before it's done growing, it's known as a protostar. The technical term for that is a T-Tauri star. You're going to see this word again, including on your test. Go ahead and write down that a T-Tauri star means a protostar. That is a star that has condensed enough where fusion is started, but it is still collecting material, so it is still getting bigger and bigger and bigger. Remember, the fusion that's happening in the core of a star is when two deuterium atoms, or deuterium and tritium, smash together to create a helium atom. Along with that comes a ton of energy, because the helium atom weighs a little bit less than the mass of all of the hydrogen atoms that went into making it. That extra mass gets turned into energy, quite a bit of energy, using E equals mc squared. If you remember one thing from today, the different life cycle of a star depends on its mass. The different life cycle of a star depends on its mass. The different life cycle of a star depends on its mass. The different life cycle of a star depends on its mass. The mass of the star is going to determine how big it is. It's going to determine how long it lasts. It's going to determine how hot it is while it's alive. It's going to determine how it dies. It's going to determine what it turns into after it dies. All of those things, all of them, are determined by one simple characteristic, and that's the mass. All of that material that is in that stellar nebula that's condensing into that star, depending on how much there is, that's going to determine everything about the star. The mass. The lifespan of a star depends on its mass. If you have a blue giant star, between 1 and 100 million years. A yellow star like our sun, about 10 billion years. And if you're a red dwarf star, you're going to last between 100 billion and a trillion years. These lifespans are the amount of time that star is going to last on the main sequence. Just doing a regular star stuff, the vast majority of a star's life, just chilling on the main sequence. I want to point something out too. If a red dwarf star lasts between 100 billion and a trillion years, our universe is only 14 billion years old. Is there a single red dwarf that has ever died? Nope. The first red dwarf ever formed is now, let's say, 13.5 billion years old. It's still a little kid. Like, it still has a long ways to go. So there is not a single red dwarf that has ever died. Ever. The next phase, old age of a star. Basically, when the star moves off of the main sequence. When it runs out of hydrogen in its core, it's no longer doing hydrogen fusion, now it's doing helium fusion. Helium is being fused into things like carbon or nitrogen or oxygen. And when that happens, it releases more energy. And as it releases more energy, it pushes the outer layers of that star farther out. And the star is going to expand and get bigger. As the star is getting bigger, it has more surface area. It has roughly the same amount of energy coming out, but it's now spread over more surface area, which means the amount of energy coming out of each little bit goes down. The temperature is going to go down. So even if you are a super hot blue star on the main sequence, when you start to die and expand out, because you have so much surface area that you're now spreading your energy over, your surface is going to cool down and you are going to turn into a red star. Which means every star, when it dies, will expand out and turn red. Every single star is going to turn into a red giant. Some of them a red supergiant, some a red hypergiant, but at least a red giant. Once it's expanded out and it's now a red giant, there are 3 possible ways that it could die. And which one of those 3 ways that it dies depends of course, on the mass. Mass. So the mass determines how long the star lasts. It determines how hot it is. It also is going to determine which type of death is going to occur for that star. If you have a small mass, small to medium, our sun is a small star. Red dwarfs are small stars. What's going to happen is they're going to turn into a white dwarf. Basically, the outer layers get so far away from the core of the star when it turns into a red giant, those outer layers just kind of float away. Gravity's not strong enough to hold on to those outer layers anymore, and they literally float away from the star. And what's left over is that core that's being held up by electron degeneracy pressure. There's no longer any fusion going on. It's simply being held up by electron degeneracy pressure, and it's radiating out the heat that's left over from being the core of a star. So the reason that we can see it is blackbody radiation. Because it is so hot, it's glowing with that thermal energy. And then in 10 undecillion, I looked up how long this many years was, 10 undecillion years later, it will turn into a black dwarf, which is basically just a dark, very dense core of a star. A star like our sun will be able to fuse helium into carbon. A lot of the material that is in a white dwarf is carbon. And when it cools down, it's going to be a big giant lump of carbon, also known as a lump of coal. Our star is going to die in 10 undecillion years as a giant, dense lump of coal. If you're a large O-class star, or maybe even an A-class star, you are going to die in a supernova. We're going to get into what a supernova is and how it happens in a few days, but it's basically a star that is so big that when it runs out of fuel in the core to push out, it collapses on itself, and it collapses so fast that it bounces off of the core and explodes out. If you are a large star, you're going to explode as a supernova, and you are going to end as a neutron star. A neutron star is basically an object the size of a city that is made of all neutrons, just like the core of an atom. It's basically an atom that is the size of a city. It is incredibly dense. It's so dense we don't really know what's going on inside of a neutron star. But if a neutron star is spinning very, very fast, they're going to be giving off X-rays, and we call those a pulsar because it seems to pulse, almost like a lighthouse that spins and we can see it and then not see it and then see it and not see it. A pulsar is a spinning neutron star. So when you hear the word pulsar, they're talking about a neutron star that is spinning. Finally, the biggest of the big stars, a star like UY Scuti or VY Canis Majoris or Westerland, the absolute hypergiants. They're going to run out of fuel in their core eventually, and they're going to collapse down and bounce off and cause a supernova to happen just like before. The difference is that because they are so big, they actually collapse their core down into itself, which doesn't make sense and breaks the rules of physics, and what we have left over is a black hole. We're going to talk about black holes more in a few days as well, because they literally break the universe. But if you are big enough, after the supernova, you're going to be a black hole. Which means, starting out as a stellar nebula, you can either be an average-sized star and turn into a red giant, end as a planetary nebula, and eventually a white dwarf. But if you are big enough, you're going to be a red supergiant, or maybe a hypergiant, and you're going to go supernova. And then depending on your mass, you're going to end up as a neutron star or as a black hole. So there are 3 ways that you can die, and all 3 of those ways depend on your starting mass as a star. Depend on your starting mass as a star. Depend on your starting mass as a star. Make sure that you have each one of these things listed on your flowchart for a low mass star. For a high mass star, make sure you have each of these on your flowchart. I hope you guys know who this is. If you don't, this is Mel Gibson playing William Wallace, who is the star of Braveheart. He is a Scottish fighter, and he has a really neat accent. The next video that we're going to watch is a guy who sounds just like Mel Gibson in Braveheart. So real quick, let's listen to Mel Gibson.
Would you be willing to trade all the days from this day to that for one chance, just one chance, to come back here and tell our enemies that they may take our lives, but they'll never take our freedom?
And now we're going to listen to an astronomer who talks about how stars live and die. It sounds just like Braveheart. One of the coolest accents we're going to hear this year.
Well, way out there in space, there's huge clouds of dust and gas. And if one of those clouds of dust and gas is massive enough, its own gravity causes it to start to collapse. So it falls in on itself, and towards the centre of that cloud, it gets denser and denser, it gets hotter and hotter. And eventually, the particles that the gas and the dust are made of are brought so close together that they start to stick together, they start to fuse. That's the energy source of a star. The star switches on and begins to shine.
Inside every newborn star, hydrogen atoms are fused together to make helium. This process is called fusion, and it creates the energy that powers every star. What happens to a star during the rest of its life depends on how massive it is at its birth.
A star like the Sun is in a delicate balance between gravity, which wants to make the star collapse in on itself, and the pressure that pushes outwards that comes from the energy that's been produced in these fusion reactions happening at its core. However, at some point in the future, the hydrogen runs out, and at that point, the core of the star will start to collapse in on itself under its own weight. It gets denser, it gets hotter, until a point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing helium atoms together and making carbon and oxygen the next heavier elements in the periodic table.
As the star begins to fuse helium, it creates more energy, and that causes the outer layers of the star to expand. One day, our sun will grow so large it will swallow up the inner planets of the solar system, out as far as the Earth. It will become a red giant. For the sun, this will be the beginning of the end.
What happens is, as the outer layers of the star get farther and farther from the middle, the force of gravity that they feel is getting weaker and weaker. And actually, the star loses hold of its outer atmosphere. Its outer atmosphere drifts off out into space. It expands out to become a planetary nebula. And they're some of the most beautiful objects in the universe.
Once the outer layers have drifted away, all that is left of the star is its core.
A white dwarf star is the dead remnant core of a star like the Sun at the end of its life. What's left behind is something that might weigh as much as half the mass of the Sun, but it's only about the size of the Earth. So it's an incredibly dense object, it's dead, there's no nuclear fusion going on it anymore, it's incredibly hot, but then over millions of years it will gradually cool down to become a black dwarf.
Some stars, however, are much more massive than the Sun, and they lead very different lives. They are able to fuse heavier and heavier elements inside their core. The star gets bigger and bigger. Some grow up to 1,000 times the size of our Sun, until it has fused elements all the way up to iron.
And once we've formed an iron core, there's no more energy can be got from fusion. That core collapses. The rest of the star starts to collapse in after it, but then it bounces off. There's a huge shock wave, and in just a second, bang! The outer parts of the star are blasted off into space in a huge supernova explosion. These supernova explosions are so powerful that when one of these stars explodes, it can actually outshine the whole galaxy of which it's part, a galaxy of maybe 100,000 million stars.
For these supergiant stars, all that is left is the super-dense core, known as a neutron star, an object that can have a mass greater than our Sun, but be less than 20 kilometers across. But for the most massive stars of all, we think when the core collapses, the gravity is so strong, it becomes a black hole, from which not even light can escape.
So stars are actually the places in the universe where the elements are created.
After the Big Bang, our universe contained only hydrogen and helium. All the other heavier elements were therefore fused inside stars.
The amazing thing is that virtually everything you see around you was made inside a star billions of years ago, before the Sun and the planets were formed. And when that star died and blasted its guts out into space, that formed the raw materials from which our Sun, the planet Earth, and indeed ourselves were made. And actually, I think that ultimately that's one of the major reasons why I think understanding stars is crucial, because it's actually telling us where we came from.
The different life cycle of a star depends on its mass. The different life cycle of a star depends on its mass. If you guys could go back and answer the question of the day, I'd appreciate it.